I want to review what we know about load, shear, and moment diagrams. When you were in structures class, you worked on especially shear diagrams and moment diagrams, and we'll use them when we go on next time and talk about section modulus. So these diagrams are a useful tool for finding out where is the maximum shear in a beam, but especially where is the maximum bending moment within a beam. Here's a real sketchy one that I just scribbled out with a pencil. When you put a load on a beam, as you know, the beam bends. Well, that causes stuff to happen inside the beam. This load, as it's trying to bend the beam, that's really a kind of moment, isn't it? It's force times distance. Stuff is trying to rotate in here. And at the same time, it's also causing the thing to sag. That's called deflection, and we'll look at that, I think, the last week of the term. Well, no, maybe next week. What you should be concerned about is where is the bending moment maximum? Because if a beam is going to fail, it's going to fail at the place where the bending moment is maximum. In this scribbly diagram, it happens to be shaped like a triangle, shaped like a mountain, and in this particular beam, it happens to be 80,000 foot-pounds. So we would be focusing on that point right there when we're thinking about this particular beam. Well, we can put a load on a beam in all different ways and locations, and I've given you a useful handout from AISC, the American Institute of Steel Construction. In their steel construction manual, they have a collection of diagrams like this, and I think the handout is 7 pages, and each page has 6 different possible ways a beam could be loaded. So you have lots of choices. This is for your reference in the future if you want a quick way to look up how these things work. So here's an example. In this particular example from AISC, we see the load at the top. So this is a simple beam, which means there's a support at each end. It's got one concentrated load, and it might or might not be in the middle of the beam. It's just somewhere. So 2 supports and 1 load somewhere in the beam. Below that, they show you the shear diagram, which you might recall from structures class. And below that, and I just want to say, they show you what shape the shear diagram should be. So it's not slopey or curvy, it's just blocky rectangles. Then below that, they show you what shape the moment diagram should be. And if you study this a bit, you'll notice that the peak of that moment diagram lies right where the load comes down on the beam. Alrighty, so now we know what shape our diagrams should be. Then they show you a formula you can use to figure out the maximum bending moment or any other thing like the shear without having to use that graphical method which we used last term. And we'll look at that in just a second. So here's one with a simple beam with a support on each end and a load somewhere. Here are some more. Here's one simple beam with a load that happens to be smack in the center. So there's a simplified formula you can use. Here at the bottom is what happens if you have 2 loads. And you have seen some beams that have 2 loads on them. So here's what you can do with that. And here's the shape of the diagram. Load jumps up, shear jumps up, continues over until the first load, then it jumps down, shear continues flat until the next load, then shear jumps down again, continues over to the end, and jumps back up to 0. We had one like this last term, as I recall. Then in this example at the bottom with 2 loads, what does the moment diagram look like? Well, it's like it's a trapezoid. It's like a Central American monument shape. So goes up with a slope, then straight across at the top, then down with a slope. And here is a line with a formula for how big is that maximum moment in between the loads. Then here are some more. I think we kind of looked at, these are just, the top 2 are just variations on some load somewhere on the beam. Here at the bottom, number 12, is what happens if you've got a cantilevered beam with a distributed load on it, and then there's a support at one end. Oh, sorry, not a cantilever. I'm looking at the wrong one. This one has 2 supports, one support at one end and then a fixed support at the other end. So this one gets a little bit fancy. The one in the lower left corner is a cantilevered beam, which has a distributed load. So this is like a balcony sticking out from your building with a concrete floor on it. And below that load diagram is a picture of what shape your shear diagram will be. Notice it's slopey all the way down. And below that is a picture of what shape the moment diagram will be. The shear was slopey, so the moment is curvy. And here is the formula you can use for figuring out how big is the moment at its maximum point. And the maximum point could be above the 0 line or below the 0 line. We don't worry about negative or positive, we just worry about how big is the number for the moment. Here's an example that we looked at in structures class, and back in those good old days we used area to figure stuff out. So in this beam we had figured out, there it is. We figured out how big are the reactions under each end, and for this guy it happens to be 8 pounds at A and 16 pounds at B. All right, so the shear diagram jumps up 8, continues over because nothing's happening. Then when it gets to where the load is, the load goes down 24 pounds, so our shear goes down 24 pounds. Then nothing happening, so we go over. Then reaction jumps up 16, so shear jumps up 16. Then when we go to figure out the moment, we just figure out what is the area inside each of these rectangles. First rectangle, when you get to the end of the rectangle, it has added up to 80 foot-pounds. So our moment diagram is getting bigger and bigger and bigger until it gets to the peak where it has accumulated 80 foot-pounds of area, so we put a point right there. And then towards the end of the beam, we're on the negative side of the beam, so our moment is going down and down and down and down until it gets to 0. That's what we did last term. Here's what you could do with that same beam using these helpful pictures and formulas from AISC. So this is a beam that has simple supports and one concentrated load somewhere, maybe not centered. Here's the formula that we can use. And the formula here, notice, says the load, so that's 24 pounds, times distance A times distance B divided by the total length of that beam. If we plug those numbers in, and you could try this with your calculator, plug these numbers in to this formula, and your calculator will tell you the answer is 80. Well, yay! That is the maximum moment we came up with. So it works. Here's another one. We did this one last term. This is our cantilevered beam with a distributed load. And if you do your graphical method, you'll come down to a maximum shear of -90 pounds. And then if you figure out the area of that wedge shape in the shear diagram, that will tell you how big the moment is. And it's on the negative side of the graph, so our moment is on the negative side of the graph. The shear is sloping, so the moment is curving. There we are. Using the Aisc formula, it says, first of all, here are the shapes you should have, yay! And second of all, here's the formula you could use. So we'll plug in W, what is the amount of the distributed load per foot? So that was 30, we'll plug in 30. The length of the beam squared, and all of that divided by 2. So here's 30, the distributed load, and times the length squared, so 3 squared. If you're plugging this into your calculator, make sure you use parentheses so that you keep the order of operations straightened out. And the reason for saying that is you do not want to say 30 times 3 and then squared all of that. That will give you a crazy number. You want 3 squared and that times 30. And then all of that divided by 2. And you might want to try that out on your calculator just to make sure you do get that same number. Okay, now next time we will go on and look at the answer to the question, so what? What do we do with these? How do we use these in a really cool simplified flexure formula to figure out how big is the bending stress?